What's up everyone? Welcome back. My name is Hako, and in this video we're jumping right into machine learning. And I know that sounds intimidating, but honestly it's way more approachable than people think. We're gonna cover the full pipeline, from exploring your data, engineering features, to training models and evaluate them. All with Python and scikit-learn. All with real code and real output side by side. As always, the link will be in the description down below to practice everything with hands-on exercises. So video plus exercise are the perfect combo. So please practice. Go to the community, it's free. So yeah, let's jump right into it. So what is machine learning? In simple terms, you can give a program data, and instead of writing rules manually, the program learns the rules from the data itself. Traditional programming is like, if the amount is greater than 1000, for example, you flag it as fraud. You write every single rule, right? But with machine learning, you give it examples of fraud and not fraud, and it figures out the patterns on its own. And the workflow is always the same. Explore the data, engineering features, split into training test, train the model, and evaluate it. That's the pipeline we're building today. Okay, before we touch any model, we need to understand our data. This is the most important step and the one people skip the most. You wouldn't cook a meal without looking at the ingredients, right? So the first three things to check are the shape and types of your data, the distributions and the statistics, and the relationships between features. Let me show you how. First thing, you load your data and look at it. The shape tells you rows and columns. Info shows you the types and missing values. Describe gives you the statistics for every numerical column. Here we have a housing dataset with 150 rows and 5 columns. 4 numeric, 1 categorical. No nulls, which is nice. And look at the describe output. Price ranges from 100K to 625K. Average around 380K. Square feet goes from 900 to 3200. This takes 30 seconds and tells you how much you are working with. So yeah, it's like very insightful. Correlations tells you which features are related to your target. Here, square feet has 94% correlation with price. That's super strong. Bedrooms is moderate at 68%, and age is slightly negative, meaning older houses tends to be cheaper. This is gold for machine learning. Strong correlations mean that the model has something to learn from. If nothing correlates with the target, no model in the world will help you. Also, check correlations between features. If two features are highly correlated with each other, like square feet and bedrooms, you might not need both. Okay, feature engineering. This is where you transform raw data into something the model can actually use. Models needs numbered, so categorical columns like neighborhood needs to be converted. One hot encoding creates a binary column for each category. So if you have 5 neighborhoods, you get 5 new columns, each with a 0 or a 1. The other option is label encoding, which assigns a number to each category, but that implies an order, which can mislead the model. Rule of thumb, use one hot for categories without order, like city or color. Use label encoding for ordered categories, like small, medium, large. Feature scaling, this one's very important. Some algorithms are sensitive to the scale of your features. If square feet goes from 900 to 3200 and bedrooms goes from 1 to 6, the model might think the square feet matters more than the other because the numbers are bigger, right? So that's when StandardScaler comes in. StandardScaler centers everything to mean 0 and standard deviation to 1. Min-max scaler squishes everything to 0 to 1 range. And here's a critical rule. Feed the scaler on training data only. Then transform both train and test. If you feed on all data first, information from the test set leaks into training. That's called data leakage. And it will make your results look better than they really are. Okay, train test split. This is non-negotiable. You always hold out part of your data that the model never sees during training. That's how you test if it actually learns something useful, or if just memorize the answers. Okay, so 80-20% is the pretty much like standard ratio. It's a standard split. So random state makes it reproducible. We use it number 42 for random state. It's just a standard, right? Same split every time you run it. And stratify is crucial for classification. It makes sure both classes are represented proportionally in both sets. Without stratify, you might accidentally put all the rare cases in training and none in test. Your test results will be meaningless, okay? So keep that in mind. Okay, cross-validation takes it this further. Instead of one split, you do 5. Each time a different chunk is a test set. So every row gets tested exactly 1. The result is 5 scores instead of 1. You take the mean and the standard deviation. The mean tells you how good the model is on average, and the standard deviation tells you how stable it is. If the standard deviation is high, the model is inconsistent. It performs well on some faults and badly on others. So use cross-validation when you have limited data or you want a more reliable estimate. Use a simple how load when you have plenty of data. Alright, our first model, linear regression. Simple. It draws a line through your data that minimizes the distance between the predictive and actual values. The equation is simple. Price equals some weight times square feet, plus some weight times bedrooms, plus some weight times age, plus a constant. 3 lines of code. Create the model, feed it on training data, evaluate it on test data. The score method gives you R squared, which tells you what percentage of the variation in price the model explains. An R square of 85% means that the model explains 85% of the variation. That's solid for a first model. The coefficients tells you what the model learned. Each number says, if this feature increases by 1 unit, how much does the price change? Holding everything else constant. So square feet coefficients of 118 means each additional square foot adds $118 to the price. Bedroom coefficients of 14,656 means each extra bedroom adds about 15K. And age coefficients of negative 736 means each year of age reduces the price by $736. This is incredibly useful because it's not just a prediction, it's an explanation. You can actually understand why the model makes the prediction it does. Okay, beyond R squared, we have mean square error, root mean square error, and mean average error. Mean square error is the average of square errors. It punishes big mistakes more. RMSE is the square root of MSE, which is brings us back to the original units. So in this case, dollars. Okay, so MAE is the average between absolute error. It treats all errors equally. If RMSE is much higher than MAA, that means you have some bigger outlier predictions throwing things off. Okay, so here our RMSE is about 25K, meaning on average our predictions are off by $25,000. 4 houses prices 150K to 625K. Okay, that's not terrible. Now let's switch to classification. Instead of predicting a number, we're predicting a category. Is this email spam or not? Will this customer churn or not? This is binary classification. Logistic regression is the go-to first model for this. Despite the name, it's for classification, not regression. It uses the sigmoid function to squish any number into a probability between 0 and 1. The API is identical to linear regression. Fit, predict, score. But now scores give you accuracy instead of R squared. Okay? Here's a big trap. Accuracy can lie to you. Imagine a fraud detection model. 98% of transactions are legit. Only 2% are fraud. A model that always predicts not fraud gets 98% accuracy. Sounds great, right? But it catches 0 fraud. Completely useless. That's why we need the confusion matrix. It breaks down predictions into 4 categories. True positives and true negatives are correct. False positives are false alarms. False negatives are missed cases. From these 4 numbers, we get precision and recall. Precision answers of everything I flagged, how much actually was positive. Recall answers of everything that was actually positive, how much did I catch. This is the decision framework. When a false positive is expensive, like blocking a legit transaction or sending a patient to unnecessary surgery, you want high precision. Be careful about what you flag. When a false negative is expensive, like missing a cancer diagnosis or letting a fraudulent transaction through, you want high recall. Don't miss anything, even if you get some false alarms. Okay? F1 score is the balance between both. Use it when you care equally about precision and recall. And ROC-AUC gives you an overall picture of how good the model is at separating the class across all thresholds. ROC is receiving operating characteristic and AUC is area under the curve. Just state that. Here's the full classification evaluation pipeline. Train the model, get predictions, and then pull every metric at once with classification report. That one function gives you precision, recall, F1, and support for each class. Confusion metrics show you the raw numbers, and ROC-AUC score gives you the area under the ROC curve. 0.5 means random, 1 means perfect. This is the standard evaluation pattern. Every time you train a classifier, run this, no exceptions. Let's tie it all together with a complete project. This is a predict house prices from scratch, very basic project. The full pipeline is one place. Start with feature engineering, create total rooms from bedrooms, plot bathrooms, then split, scale, train, and evaluate. Notice that the scaler is fit on train only. This is the exact pattern you'll follow for every machine learning project. The model might change, the features might change, but the structures stay the same. Explore, engineer, split, scale, train, and evaluate. Okay? That's the complete ML foundations. You know the full pipeline. From exploring data with pandas, to engineering features, to splitting data properly, to training both regression and classification models, and evaluating them with the right metrics. The patterns is always the same. Explore, engineer, split, train, and evaluate. Okay? So the model and the metrics change depending on whether you are predicting a number or a category. But the workflow doesn't. In the next model, we'll get into decision trees, random forest, gradient boosting, models that can capture way more complex patterns. But everything we covered today is the foundation for all of that. That's it for ML Foundations. Remember, hands-on exercises in the link down below. Go practice because that's where the real learning happens. If it was useful, like and subscribe. We have a lot more coming, so stay tuned. Thank you for watching. See you in the next one.